All right, now say you want to tune into my favorite radio station, KSBC, at 88.7 megahertz. So if KSBC is at 88.7 megahertz, which it is, what wavelength does that mean that you'd have to be scanning for? So if you're scanning for KSBC at 88.7 megahertz, what wavelength would that mean that we're looking to be able to pick up? Well, once again, we use the exact same thing, just slightly different. Frequency times wavelength. Well, the velocity we're dealing with for electromagnetic waves is 3 times 10 to the 8th equals whatever frequency it is. So in this case, 88.7 megahertz, 88.7 times 10 to the 6th hertz, because it's mega, times the wavelength. So the wavelength is going to be equal to 88.7, oh, whoops, sorry, put that the wrong way on. 3 times 10 to the 8th divided by 88.7 times 10 to the 6th, which means that we're going to be looking for a wavelength that's 3.38 meters. That's pretty big. It's really interesting to compare how much difference there was between the wavelength of that green light, tiny, tiny thing, 525 nanometers, to 3.38 meters. That's practically 2 of me standing on my shoulders. So that's a really tall wavelength. That means that if you're going to want to pick it up, you've got to have some way of being able to see all that information in that really long wavelength passing by you, which has to do with the way waves work, but we once again aren't going to quite get into that. But 3.38 meters, really long wavelength because it's got a really small frequency compared to some of the other ones. All right, hope that gives you some idea of how light works and possibly spark your interest in some of the other many, many interesting things to look at. All right, thanks. We'll see you later at Educator.com.